Okay, hello, it's Kerry Gallagher. What I want to present in this little session is just a quick overview of the capacities of QTQt in terms of what kind of data can be used, what kind of modeling can be done. Without actually looking at running the program, we might have a quick look at that at the end, just to look at the menus and what possibilities there are actually in the user interface. So QTQt, or QTQt, often called it strictly, I think it's QTQt, stands for quantitative thermochronology, the first QT, and the second is Qt. It's a programming environment which lets us build the user interface and do all the graphics and so on. The icon is this chimpanzee, which has no significance at all. And the idea in QTQt is we can have multiple samples with multiple data types, multiple methods, for example, fission track analysis, helium diffusion, argon, various different types of data. And we try to understand the thermal history contained in those data, either by inverse modeling, but we can also use forward modeling. And in fact, in practice, perhaps a combination of those two is the most useful approach to take. In terms of the data types, well, you can deal with up to 50 samples, and the idea is those will be in general in a vertical profile or in a well, so they've effectively experienced the same form of thermal history. It's just samples which are either deeper in a well or lower elevation in a vertical profile will have been hotter than the samples which are shallower in the well or at higher elevation in the vertical profile. And for each of those 50 samples, you can have different data types. So you can have apatite fission track analysis. We can allow for multi-compositional annealing models, zircon fission track analysis, and even monazite fission track analysis, which is very recent and perhaps still requires a little bit of work. Apatite helium, zircon helium, pretty well established methods now. And you can incorporate up to 30 single grain ages for each sample. And you can allow for different radiation damage models. You can allow for broken grains. And the other standard approaches for modeling helium diffusion data in minerals. Vitronite reflectance, VR, there's two standard models, easy row and basin row, but you can also specify your own kinetic parameters based on those kind of models, formulations. Helium 4-3 spectra, where you can allow for zonation in the parent elements, uranium, thorium, samarium. Argon 4039 multi-domain diffusion spectra. In fact, you can simulate any simple diffusion problem with different geometries, so either in a sphere, in a cylinder, an infinite cylinder where the long axis is infinite, or a slab defined by two surfaces, which might be useful for simulating mica. And you can put in specific diffusivity parameters as you like for those three different geometries. You can also model single grain age, single crystal age profiles, so a range of ages measured across a grain, a single grain, to have an age profile which reflects to some extent the diffusion profile inside the grain. And finally, OSL optically stimulated luminescence data. There's one published model, I think, that's been incorporated into QTQt, but I think that's probably not particularly widely used, but it's there. So first recommendation, though, is read the user guide. It's about 90 pages long. There's a lot of information in there that, it's not the kind of thing you probably read from start to finish, but if you have a particular kind of data, say, for example, apatite helium data, you could look at the section on apatite helium data and see the kind of things that you might want to do, how to deal with them, how to input data, and various other aspects related to particular data types. And if you have a problem, you can always contact me anyway. There's my email address is there under the chimpanzee. So before we start, let's think of sort of the rationale behind why we're using geochronology. We're usually trying to understand or answer some geological questions. about the thermal history of rocks or related to geological processes. And this diagram is really just trying to say, okay, we start here at the top with our data, which are in general good quality, we hope. We sort of understand how we collect the data. We perhaps understand some of the variations in the data, what causes dispersion. And we should look at our data closely before we approach any modeling. Try and understand if there are problems in the data or not. But once we've done that and we want to get into trying to model something, we need to have some kind of temperature sensitive predictive model, which in our case here is either some kind of annealing model or some kind of diffusion model or something for vitrinite reflectance, for example. It's a mathematical model that lets us predict what we'd expect to measure, for example, for a given thermal history. Okay? And clearly, to use those models, we need to specify a thermal history. So the data production and modeling approach sort of goes in this sense from top to the bottom. In a way, the modeling approach using inverse modeling does the same. We start with the data and we try and extract the thermal history from the data. And the two common software modeling packages used in thermochronology, QTQt and Hefty, basically stop there. So we're trying to extract a function, which is the temperature history, usually a series of time temperature points which are joined up by straight lines to create a continuous thermal history. And we make a prediction of what we'd expect to measure for different data types with that thermal history and compare those to our observed data. And in that case, there are no physics of there's no physics of heat transfer, there's no thermal diffusivity, heat production, those kind of things. We don't have to worry about 1D, 2D, 3D heat transfer and so on. So in a sense, really just trying to extract the thermal history directly from the data is we're resting as close as possible to the original data, and the filter is really those predictive models for annealing or diffusion. But there are other software such as P-Cubed, which are much more sophisticated, incorporate the physics of heat transfer, let us model things in 1, 2, 3D, require more parameters to be specified. Those parameters are relevant to the heat transfer problem, so properties like the thermal conductivity, the thermal diffusivity, perhaps heat production. We might need to worry about advection, so we need to specify velocities of transport. We need to specify boundary conditions like the heat flow into the base of the crust or the base of the lithosphere, depends what we're interested in, the surface temperature history and so on. So with those kind of sophisticated software, they're very useful, but we're a little bit further from the data than just trying to extract the thermal history. And then some of the questions that we're actually interested in terms of earth science problems are about how topography evolves, or how erosion occurs, how drainage evolves, how sediments are produced. And all those questions here down at the bottom of this figure are much more distant from the original data than just the thermal history. So the interpretation stage is a whole series of steps to get to the interesting stuff, if you like, that take us further and further away from the original data and require more and more assumptions usually to produce some kind of estimate of, for example, erosion rates and so on. So really the QTQt Hefty approach is just, we're going to stop really at the thermal history, and then the next stage of interpretations is another dimension that we're not going to worry about. Okay, so in terms of this thermal history modeling, QTQt can deal with single bedrock samples, so just one sample by itself that can have, as I said, these various types of data. And the method that is used in QTQt is published in this paper in the Journal of Geophysical Research in 2012. This is transdimensional Markov Bayesian inverse approach using Markov chain Monte Carlo. And I call this approach with a single sample 0D, 0 dimensions, just one sample by itself. What's the thermal history? And that's a relatively non-unique problem. Depends on the data, of course, but one sample by itself doesn't tell us a huge amount. We can deal with multiple samples, which is better because the idea there is we have samples that we can group together somehow that have some kind of common thermal history information. Then that common thermal history information should be reinforced for more samples, and the sort of random noise aspect of the data should tend to cancel out because it's random. So in principle, combining samples is a good idea because we reinforce the real signal and we remove them, or we reduce the effect of random aspects. So one way of dealing with multiple samples is in vertical profiles or in boreholes, where, as I've just said earlier, all the samples have experienced more or less the same form of the thermal history, just depending on where they are in the vertical profile and the borehole. The actual temperature values might be different, but the shape of the thermal history should be more or less the same. And that approach was presented in terms of describing how that works in a paper in 2005. And I call that a 1D approach. We've got one spatial dimension, the vertical dimension, and we group samples according to their elevation or depth in the vertical dimension. So that approach doesn't let you deal with faults in that vertical section. So you can't at the moment deal with that kind of problem with QTQt. Another approach is dealing with spatially distributed samples, which I call 2D and 3D, where we can have samples distributed in 2 dimensions spatially, so X and Y, or longitude and latitude, or in 3D where we have X, Y, longitude, latitude, plus elevation. And we looked at that problem a few years ago as a paper in 2006, and we're actually revisiting that problem at the moment to incorporate that approach into QTQt and actually improve the approach. It was relatively simple, the approach we developed, but in the process of trying to improve that. And the last thing we can do is deal with detrital samples, which can be incorporated with the more classical in situ or bedrock samples, where we have sediment detrital samples from a catchment. And the idea is we can try and reconstruct the thermal history of the catchment using just a detrital sample, or that can be combined with bedrock samples in situ in the catchment. And that was published, that approach was published in EPSL in 2020 with Mauricio Parra. Okay, so just to explain that a little bit more, this 0 to 3D modeling. So 0D is just one sample by itself. So these little dots represent samples. You just take one sample here, for example, and say, what's the thermal history? That's okay. As I've said, it's a good idea if we can try and combine samples to reinforce the real signal in the sample. So the idea of a vertical profile is a bit like this, where we have samples at different elevations, and we say they've got the same form of thermal history, but the sample here, say this one, is the lowest elevation. That would be the coldest sample, so it would be equivalent to this thermal history. And perhaps this sample here, which is the highest elevation, sorry, I've got that the wrong way around, will be the coldest, and the lowest sample will be the hottest. Sorry about that. And we look for a common form of thermal history, grouping all those samples together. And we have an extra additional parameter or parameters to introduce is the difference in the temperature between the top and bottom sample as a function of time, that we often call the offset, or that could be chosen in terms of a temperature gradient with elevation. So that's this 1D problem I mentioned. And then the 2D problem is actually when we have these samples we can group together spatially. And in principle, we could take all our spatially distributed samples and group them together. But if there are differences in the thermal history, either because of faulting or some other factor, so those differences in the thermal history can be relatively abrupt if they're due to faults, for example. We don't know how to group the samples together. So the general problem is how do we group those samples to different samples together, and also what's the thermal history. So the vertical profile problem, just to explain that, is like this. We have a series of samples at different elevations. which could be also in a borehole, so that would be depth. And as we go lower or deeper into the earth, we expect the samples to have experienced hotter temperature histories, or at least until very recently. So we can measure our data. It's just an example of fission track, appetite fission track ages in red, and the mean track lengths in blue. For a vertical profile is a synthetic data generated where we know the thermal history in the end. So the question is, can we take those data and reconstruct the thermal history? But if we start with each sample by itself, so to treat each sample independently, we can model the thermal history. And now here, just to explain what we've got, the black dotted lines here are the true thermal histories for the top one is for the coldest sample, the highest elevation sample, and the bottom one, black dotted line, is for the hottest, the lowest elevation sample, and all the other samples in between, elevations in between, just a parallel to that thermal history. It's the form of the thermal history is important. When we model each sample independently, so that the coloured lines here from red to blue, the numbers of the elevation in our vertical profile in meters. So the red is the hottest one, the blue is the coldest. We take each sample, we model the data, synthetic data, and look at what do we get as a thermal history. And you see that sort of the red ones tend to be hotter and the blue ones tend to be colder, but it's a bit confusing to understand what's going on. We see the thermal histories for different samples cross over. So it's a little difficult to understand those results. But when we look on the right, something important that we should always look at when we're doing modeling is how well we fit the data. And the blue line is the predicted fission track age profile, and the circles that are the observed values or the data. And the same in red is for the red is the fission track age profile, and blue is the mean track length. The lines are the predictions, and the solid circles are the observed values. So we see we fit our data very well, and that's good, but it's quite hard to understand these results because the thermal histories cross over and it's a little complicated. If we group all the samples together and say, well, we're going to make a condition that we predict the sample at the top is always the coldest and the sample at the bottom is always the hottest, and we're trying to find the form of the thermal history and also the temperature difference between the top and bottom samples. And now we see the black lines, solid black lines in this case, are the true solution, and the blue and red lines are the reconstructed solutions. On the right is the data fit. In fact, in this case, I've added a little bit more data, so some appetite helium data, but it doesn't really change if I use just the fission track data. But you see now that the results are much more coherent. It's the cooling profile for that whole vertical profile. We get the 2 periods of cooling well resolved. And just on this picture, well, it's there, the pink lines on the red curve, around the red curve, and the light blue lines around the darker blue curve. They're what we call the credible intervals, which is the uncertainty around the thermal history. Right. Okay, and this is 95% probability. Okay, but that doesn't really matter too much. The point is grouping samples together helps us resolve the thermal history better than treating samples independently. And this idea of 2 and 3D modeling, which we call partition modeling, is if we have samples spatially distributed, we might think samples that are close together should have the same thermal history. But in fact, if we have a fault between 2 samples that could be very close, their thermal histories could be very different. So the question then is, how do we try and group samples together spatially if we're not sure whether they have the same thermal history or not? So we published an approach for this a long time ago, in 2006, and this is just taken from that paper. It's a simple synthetic example, again, where we have these 4 partitions, 1, 2, 3, and 4, spatially, x1, x2, as x and y, longitude, latitude. And the thermal history in each sample is relatively simple, but different. And we produce synthetic data, those thermal histories. And then we say, okay, let's remove, say we don't know where those different partitions are. We don't know how the samples are grouped. and we don't know the thermal history. So the problem is how do we group the samples together and at the same time infer the thermal history? And I won't go into how we do that, but the result in that case is, this is again from the same paper. These coloured lines on the, or coloured diagram on the left shows the probability effectively of having a boundary or a partition boundary between the samples. So we see where the samples are closest together, we actually resolve those boundaries pretty well. Where the samples are a bit further away, for example up here, we don't resolve the boundaries particularly well. But effectively we do recover the true solution. And on the right, this is a relatively crude method we presented at that stage. We recover pretty well the thermal histories in each partition as well. Okay, so that's work that's something that we're looking at incorporating into QTQt at the moment. It's sort of halfway there, it's not finished yet. And the main difference is we want to incorporate this trans-dimensional thermal history modeling into this approach. The paper we published here was the thermal histories with fixed dimension. Okay, so that's work in progress. Another example of something that is not obvious but can be dealt with in QTQt is here. It's effectively a horizontal profile. This is some data from a paper by Joe Colgan from the USGS in the Basin Range, where he collected a series of samples across a granite that were from a tilted fault block. So these samples are all more or less at the same elevation, but we can see the idea. We start at the bottom of this diagram on the right here. The green line just here is effectively our horizontal profile on the left. And if we reconstruct the tilted fault blocks, we put back what's been eroded here, this little triangle there. And then, if you like, unrotate the blocks. This is what the green line shows, what we expect the horizontal profile today to represent prior to the faulting and rotation. So the samples on the left here were shallower, and the samples on the right were deeper, closer to the fault. And it's shown a bit in this diagram taken from Joe's paper here, the same idea. So he reconstructed effectively these paleostructural depths. But we don't really need to worry too much about that in QTQt, because we're just worried about temperature and time. Okay, and this temperature offset we don't really need to worry about depth. So we can take those data and we say, well, let's pretend it's a vertical profile. What we expect to happen during this rotation is the temperature difference between the top and bottom samples should start large, as in the top here. This little bit here is the maximum temperature difference. By the time we get to the present day, the temperature difference is 0 because they're all at the same temperature. So we can let this temperature offset parameter change as a function of time. Okay, so this is effectively what's said here. If we just quickly look at the results, this is from this paper in JGR in 2012. And you can see we fit the data very well. We come down to the bottom, the appetite helium data and appetite fission track data, we fit pretty well. Mean track lengths, not perfect, but we get the right kind of form. In this case also, we allowed for the kinetic parameter for fission track annealing, this dpar, to vary a little bit too. These are the estimates of the dpar that reproduces our inferred thermal history. And you see these grey curves here on the right in detail. These are from Joe's paper, which apparently took quite some time to reconstruct those. And you see the parts of the thermal history. I'm not going to go into details. It's explained it in the paper in more detail, where the structure in the original reconstructed thermal history, we get the same kind of result. And so we see these strange temperatures at 500 degrees here. We're not saying that the data are telling us. The data in this case tell us very little about the temperature history above 100 degrees, 120 degrees probably. But it's all the part above here that tells us that the data informing us about the thermal history here. But we just see at the time when this sample or this temperature gets to about 500 degrees, in fact, it's the samples that are shallower or colder that are constraining our thermal history in here. So it's these 1, 2, 3, these grey lines. plus the blue line, are telling us something about the thermal history at that time. The samples below this 120-degree line really tell us nothing until they cool below that value, either around about 35 or around 5 million years. Anyway, it's just an example of a slightly different application of this multiple sample method. And the final thing is this idea of using detrital samples. So the idea of the vertical profile, I've already said, is we have samples up the side of a valley, for example, in bedrock. We can collect our data from there, and we can know that these are helium ages and fission track ages, perhaps the different values at different elevations, perhaps reflect different grain sizes or different annealing kinetics, different compositions. So we can collect all of these data, and the idea of that, as we've already seen, we can take those data and we can try and recover the thermal history, with the blue thermal history being the sample at the top, the coldest, and the red, the sample at the bottom, that's the oldest, the hottest, sorry. And the idea of this detrital approach is if we have a sample here at the outlet of a catchment that's sampled somehow, this vertical profile, and we can get a spectrum of detrital ages in our sample of fission track and helium or both, and we can use other methods too in principle. And clearly what we measure in the detrital sample is going to be a function of the elevation age profiles for the different types of methods. And the question is, can we effectively do the same as we do with an in situ vertical profile? Can we take the detrital data and try to reconstruct this vertical profile's thermal history? And so in principle, yes, you can. And this is published in this paper in EPSL in 2020. This is just an example from that, from a real data catchment in Colombia, where we had some in situ bedrock data, we had some detrital data. It's just fission track data in this case. And just at the bottom here is what we call the topographic sampling function, which is the way that the catchment is sampled as a function of elevation, the vertical profile. So it's not necessarily uniformly sampled, depends on what kind of erosion processes are operating. And we try and estimate that sampling of the topography in the catchment at the same time. And that's best done when you have the detrital data and in situ bedrock data, which we did have in that case. So the bottom left is the in situ bedrock profile data, and the top right is the detrital fission track data. So if you want more details on those, go and look at the papers there. So to use QTQt, there's different stages clearly. So we need to build our data files if we don't have them already. We can use existing data files if we have them, clearly, someone sends us them. And we can run models in forward mode where we specify the thermal history and see what the predicted thermochronological data will be. Or we can take the data and run those in inverse models where we try and let the data determine the thermal history. And in both of those cases, there's a very important step is to look at the output, look at how well we fit the data, look at the thermal histories, are they reasonable, add in whatever information is deemed to be useful to try and choose between different models. So what we'll do is I'll stop there, and next time we'll come back and we'll start up QTQt and we'll look at run through the menus and look at how we build data files. Okay, so I'll be back in a minute. Okay, so just very quickly as the last part of this this video, we're going to look at QTQt, just the interface, and run through quickly what there is. So when you start it up either on a Macintosh or on Windows, it should look something like this. In the background, I've got the all-important documentation. we just run through the menus, and perhaps the first one to look at is, well, we have file menu, which lets us open and build files, review different files, basically dealing with data input or results input to look at graphics. The edit menu is just a standard edit menu. The thermal history constraints is actually just lets us choose between running an inverse model or running a forward model. That later. The MCMC run menu is just where we said if we're running it an inverse model using Bayesian Markov chain Monte Carlo, we need to set some parameters. So that's done with that menu, and we can't access these menus usually before we've input some data. Okay. And the last menu is called plotting, but in that the first line in this is a series of options that you can set in QTQt. If I open this, which will be saved to your user home directory. And each time you start QTQt, it will load these options that you've chosen, which are various things of how the graphics are dealt with, how the scales are dealt with. If we want to specify for vertical profiles using temperature offset or temperature gradient, whether we want to keep all the graphics windows open, what kind of font we want on our graphics, various things that are explained in the documentation. Okay, and once you start up QTQt, it should read in your options file. It will tell you various things of where you are at the moment, what it thinks the home directory is, where it's going to write things to, and some of these parameters that are set in that options dialog, which I just showed you. Okay, so that's just the interface, and as I've said already, the documentation is all here. Quite a lot of work to put this together, so don't forget to look at the documentation. So we'll leave that there, and then next little video we'll look at how to build data files.